Welcome back to the Explainer. Today, we are jumping straight into the invisible mechanics that actually bridge two of the most absolutely vital forces in our physical world, electricity and magnetism.
You know, for the longest time, the scientific community just treated electricity and magnetism as entirely separate things, like they had nothing to do with each other. But that whole paradigm completely flipped back in 1820. Hans Christian Ørsted actually discovered, almost by accident, that a compass needle would violently deflect if you just placed it near a wire carrying an electrical current. And just like that, boom, the connection was forged.
Okay, let's dive into this roadmap. We're looking at the electromagnetism plot twist, mapping the invisible field, wires and magnetic circles, solenoids and electromagnets, and finally, the magnetic push.
So, Part 1. The electromagnetism plot twist.
Before Ørsted's big breakthrough, scientists were mostly just focused on how electrical currents produced heat. But think about how iron filings magically arrange themselves when you scatter them around a simple bar magnet. They don't just sit there. They actually align along these perfectly defined magnetic field lines, basically giving us a visual map of these completely unseen forces at play.
Moving on to Part 2, Mapping the Invisible Field.
Now, these magnetic fields, they aren't just random, chaotic lines. They're actually incredibly strict and organized. By convention, they always emerge from the North Pole and merge at the South Pole to form these continuous closed curves. And you can tell how strong the field is just by looking at how close together the lines are. Where they're really crowded together, that force is much stronger. But here is my absolute favorite rule. No two field lines will ever cross. Ever. Because if they did, it would literally mean that right at the intersection, a poor little compass needle would have to magically point in two different directions at the exact same time, which obviously is impossible.
All right, Part 3, wires and magnetic circles.
So you might be wondering, what happens when this exact same field is generated by a straight current-carrying wire instead of a standard bar magnet? Well, if you run a straight copper wire through a board and sprinkle those same iron filings, you don't get those sweeping arcs anymore. Now, what's really interesting here is you get perfect concentric circles, and they just keep growing larger as you move further away from the wire, because, as you'd expect, the magnetic field gets weaker with distance.
But how on earth do we predict the direction of those circles? Okay, I want you to actually try this with me right now. Seriously, physically hold up your right hand and imagine you're grabbing onto that straight wire. Now point your thumb in the direction that the electrical current is flowing. Notice how your fingers curl? They naturally wrap around that imaginary wire in the exact direction of the magnetic field lines. It's brilliant. We call this the right-hand thumb rule, or sometimes you'll hear it called Maxwell's corkscrew rule.
Let's take this one step further. What if we took that perfectly straight wire and bent it into a circular loop? Well, those concentric circles, they are still there, at every single point along the wire, getting bigger as they move away. But here's the cool part. By the time we reach the very center of that circular loop, all those massive arcs neatly combine. They basically add up to create straight, parallel lines. So every single section of that wire is now contributing to the magnetic field in the exact same direction right through the middle.
Let's move to Part 4 and see how this builds. Solenoids and electromagnets.
Okay, so if just one loop gives us straight lines in the center, what happens if we stack, say, 100 of them? That brings us to the solenoid. A solenoid is literally just a coil made of many circular turns of insulated copper wire wrapped tightly into a cylinder shape. And since the current in every single turn flows in the same direction, the magnetic field from each turn just stacks up. It adds together. This creates a magnetic field inside the cylinder that is incredibly uniform. It forms perfectly parallel straight lines, meaning the magnetic strength is exactly the same at every single point inside that coil.
And this brilliantly illustrates the real magic of this whole setup. A current-carrying solenoid basically mimics a natural bar magnet perfectly. One end of the coil literally acts as a magnetic North Pole, and the other end becomes the South Pole. So without digging up any magnetic rock, we've synthetically created the exact behavior of a permanent magnet using nothing but electricity.
But of course, we can take it even further. Because that field inside the solenoid is so strong and so incredibly uniform, we can actually use it to magnetize other things. If you just slip a piece of magnetic material like a rod of soft iron right inside that coil, it instantly becomes magnetized. This is what we call an electromagnet. So there you go, we've gone all the way from a simple current flowing through a wire to engineering a powerful, highly controllable magnet on demand.
Which leads us to Part 5, the magnetic push.
Now, the brilliant French scientist André-Marie Ampère realized something deeply profound.
He figured if a current-carrying wire can exert a force on a magnet, physics practically demands that the relationship has to go both ways, right? I mean, electricity pushes a compass needle, but what if the magnet pushes back on the wire? This is a real game changer. It's the absolute climax of our explainer because it introduces how we generate real physical motion from totally invisible fields.
There's a super classic experiment for this. Basically, you take a small aluminum rod, you suspend it horizontally, and you place a really strong horseshoe magnet right over it, so the rod sits smack in the middle of a strong magnetic field. Now, the second you pass an electric current through that rod, it literally jumps. It is physically displaced. The magnet is pushing back. It's exerting an equal force on that current-carrying wire. And the best part? If you flip the switch and reverse the current, the rod jumps in the exact opposite direction.
Now, if you want to know exactly which way that rod is going to jump, we've got another handy trick. Get your left hand ready this time. We're using Fleming's left-hand rule. I want you to stretch out your left thumb, your forefinger, and your middle finger so they're all pointing at 90-degree right angles to each other, okay? Now, if your forefinger points in the direction of the magnetic field and your middle finger points in the direction of the current, your thumb is going to point in the exact direction of the force, the motion. It's literally like having a built-in compass for physical force right at the end of your arm.
So the crucial point is, this isn't just some fun parlor trick with an aluminum rod. This exact magnetic push, this displacement that happens when you cross an electrical current with a magnetic field, this is the secret engine of the entire modern world. It is literally the core operating principle behind electric motors, generators, precision measuring instruments, and yeah, absolutely, even the loudspeakers and microphones you're using to listen to this very explainer right now.
We started with nothing but a wire and a simple compass, and we've built all the way up to the foundation of modern electrical engineering. It really makes you think, doesn't it? Since these deeply intertwined, totally invisible forces are out there literally powering the motors of our modern world, what other incredible unseen effects are just waiting to be discovered right in front of our eyes? Stay curious and keep looking for those invisible connections everywhere around you.